And it's going to be a bimolecular reaction, as the 2 entails. Just like SN2 is a bimolecular reaction, E2 is going to be a bimolecular reaction. And another way to think about this elimination reaction, this E2, we could think of it as a method to prepare alkenes. So in the back of our head, we can just think of it as a method we can use to make alkenes, and it's going to serve that particular purpose. We're going to get the kinetics of this out of the way. Again, they're not the most important thing for us. The rate of this particular reaction is some rate constant multiplied by the substrate concentration multiplied by the base concentration. And so it's a bimolecular reaction. That's where this 2 comes into play, and both the base and the substrate matter. So it's kind of analogous to the SN2 reaction where the substrate and the nucleophile matter. It's a contrast to SN1 reaction where we only had one term here. And so tomorrow when we look at the E1 reaction, we'll see the E1 relates to the E2 reaction. But again, I know kinetics scares and strikes fear into the hearts of many weary organic chemistry students. We're not going to do anything with kinetics in this course, just to acknowledge this particular rate, put it here, and it does have some relationship to these energy diagrams that we graph occasionally to understand transition states and other things. Let's just put a little small, demarcation here between 2 different things that we're going to draw. We're going to draw in a sawhorse projection. Just draw H, and let's draw the word halogen here. We could use the letter X here. So let's just draw a substrate like this. There's some vagueness about what's here, but let's just draw this particular substrate. The key bit is that's in a sawhorse projection. If you're not so familiar with sawhorse projections, it's okay. We're going to see their relationship to Newman projections, but we're just drawing it in this kind of a skew fashion. We can see the halogens down and the hydrogens up. Maybe this bond and this bond are coming out towards us. These 2 bonds are going back. We could have done this with wedges and dashes, but let's just draw it this particular way. And let's recall SN2. And with SN2, if we had a nucleophile, typically negatively charged, we know that the nucleophile attacks at this particular position. And then halogen is typically our leaving group, but tosylate and some other things aren't necessarily halogens. So again, this is the very simplistic mechanism for the SN2 reaction. It happens all at once. Nucleophile matters, substrate substitution pattern matters, how bulky it is, leaving group matters, solvent matters. These steps all happen at the same time. And we also know that there's an inversion of stereochemistry since the nucleophile can only attack from the backside of this carbon-halogen bond. So this is just a quick recall. And the reason why E2 gets a little bit confusing with this is that we're going to draw the same type of, I like to call sawhorse projection. If you don't know what a sawhorse is, you can look it up. I'm sure Wikipedia has a great picture of it. We're going to draw the same type of arrangement of atoms. Okay, we've got a halogen here, 2 carbon atoms, and a hydrogen. And now we're going to draw a base molecule. Let's draw methoxide. Methoxide is a strong base. It's just like sodium hydroxide. This could be sodium methoxide, potassium methoxide. Those things don't matter. But these are very basic compounds. If you look at their conjugate acids, you get water, or in this case, methanol. Those are very, very weak acids. pK of methanol or water is about 15.7, 16. So those are very, very weak acids. I drank some water this morning. I'm still living here. My throat feels fine. So it's very, very weak acids. This would be a very powerful base. And what happens when this gets basic enough, right? And there's some relationship to nucleophiles and bases, but if you really look at the definition of what makes a good nucleophile, it's not basicity. It's related to its electronegativity. But bases can also do acid-base reactions. And we're going to start labeling this carbon alpha. And we could have labeled this carbon alpha a long time ago. And we labeled carbocations alpha when we were doing carbocation rearrangements. But this carbon is the most important carbon in the molecule. It's attached to something different. And that different thing here puts plus charge here. And so this alpha position is kind of just a frame of reference. It's our most important carbon. And for elimination reactions to take place, they don't happen at alpha. If there was a hydrogen at this particular position on alpha, it would not react here, but only at the beta position. This is really, really key point. So we have to now turn our attention to this beta position. And the alternative thing that can happen is an acid-base reaction can happen here. This proton becomes slightly acidic, and even more so by this close proximity to a leaving group. Okay? So the mechanism is different. We're going to break a bond, or we're going to make a bond, break a bond, make a bond, and break a bond. And all four of those things happen at the same time. This is a simultaneous process. Or we say it's concerted. It's a concerted process or a concerted reaction. It happens all at once. And look at all the things that are happening. OH bond forms. We have a CH bond, breaks. We have a carbon-carbon double bond forming. And we have a carbon X bond breaking. So all four of these things happen at the same time by these three arrows that we've described. And the key things we're going to need to know right off the beginning is that substrates are going to be very similar to what we've had before, some sort of carbon with a leaving group. We're going to be using a strong base, and the base, instead of directly attacking at alpha and doing a substitution reaction, it goes to beta, and it does so for energetic reasons. Nucleophiles usually aren't very basic, actually, and they can't do this acid-base reaction. So nucleophile only has this particular choice, and usually it's energetically favorable. The substrates are better than the starting reagents. Base has another option, and it also makes very, very stable molecules in this particular process. It forms a strong OH bond, it forms a carbon-carbon double bond, and it's breaking one strong bond and one weak bond, but energetically this will still be downhill. But base has this added ability to do acid-base reactions. I'll keep these types of problems very, very separated on our third exam. We're going to keep in mind just this general motif that this is a strong base. So when we see this type of O-methyl, O-ethyl, or maybe OH, those three types of bases we're going to reserve in this class to do this E2 type of reaction. If we look at our notes carefully, we'll see a few of them doing SN2 reactions. We'll talk about those cases on Wednesday, I think. But by and large, when we see this type of molecule mixed with our typical substrate that we're familiar with, we're going to turn our attention away from alpha and just consider the possibility that we can do elimination reactions. When this particular process happens, the final thing we would make here, we would have an alkene, basically. All right, so we'll be forming a double bond right down the middle. One of the H's is gone, one of the halogens or leaving groups is gone, and so this is an elimination reaction. It's kind of the opposite of an addition reaction. If we had HBr to this, we go here. If we had base to this compound, we go here, and this is the elimination product where a molecule breaks into different pieces, where pieces come off the molecule going forward. There's a new facet of this particular reactivity that matters. The nature of the substrate isn't important as in SN2 or SN1 per se, but the way that this molecule lines up is definitely important. We have to have a periplanar arrangement. Periplanar just means in the same plane. Okay? Means in the same plane. So the two choices we have to have in this arrangement, I'm going to draw them both in sawhorses. Let's just draw this one here. And I'm going to draw another one, also in sawhorse projection. If you're not familiar with sawhorse, don't panic. In sawhorse, we have alpha, beta, and these are 180 degrees apart. And in this other one, we have alpha and beta. And these two atoms I'm putting in boxes are 0 degrees apart. So we're going to use Newman's today. We're going to revisit Newman's in a very simple and effective way to look at this. But There's a requirement, unfortunately, in this reaction that the beta hydrogen and the leaving group must be either anti-periplanar, which means 180 degrees, and you know anti from Newman projections. And the other possibility is this kind of eclipsed arrangement. This is called syn. You've heard that word before, same side, but it means these two things are 0 degrees. If we look down these bonds, these methyl groups would be eclipsed, these would be eclipsed, these methyl groups here would be eclipsed. Here, everything would be staggered, and we're going to draw this together with Newman projections today, so it'll be a good review for us. The anti-conformation is definitely energetically favored over the syn conformation, okay? But either one of these works, and any other conformation doesn't work. Right? So these are required conformations. We have to have these atoms this way, or the reaction doesn't work. So let's just put a note here. If anti and syn are, what's the right word, impossible? So if anti and syn are impossible, the result will be no reaction. Okay? So this is a requirement. We have to have these things aligned this way. And it's not a major deal for us, really. You'll see why as we do some problems. We're going to be able to almost always get to anti or syn conformations. We're not going to have to think about it for every single thing we try. Let's just actually move forward, do some examples. You'll see exactly what I mean.